Okay, so the first exercise kind of shows you why the dual simplex is so important. The dual simplex is extremely important because if I have solved a problem to optimality, so I have the optimal basis for a problem, I add a constraint, then there is an easy way to construct a dual feasible solution for the new problem, starting from the optimal basis of the old one. Okay, so if our workflow is we have a problem, we solve it, we add a constraint, we solve again, we add a constraint, we solve again, we add a constraint, we solve again. Dual simplex is king because it never has to restart from scratch, but it can always start from the previous basis, modify it a little bit, and then it's ready to go. And we will see, maybe next week, that this is not just an abstract scenario, the fact that we add constraints iteratively, but it is at the basis of another super important algorithm, which does exactly this. So that's why it is so important. Anyway, this is the exercise. So let be a dual feasible basis for the usual system. Okay. And show how to construct a dual basis B prime after adding the constraint equal to B. Okay, so this is even more generic. So I don't even have to have an optimal solution of my system in order to be able to construct a dual feasible basis if I add a constraint. I can just start with an arbitrary dual feasible basis of my system, and I can easily construct a new dual feasible basis after adding a constraint to the problem. Let's see how. So first of all, this constraint is not in standard form. We have to bring it in standard form because our notion of basis is only defined in standard form. So we rewrite the constraint that we want to add this way. And we add this new variable here as a variable in the basis. So in other words, we consider B prime as this. So this is a trivial operation to do. So we have our starting basis for our original system, and then we just add to it one row and one column. So there are all zeros here. Here there is the new variable that we have just introduced in order to bring this is standard form. And here we just have the coefficients of the basic variables in the constraint that we are adding. Okay, now the claim is that this is a dual feasible basis. Well, first of all, it is a basis. This should be clear, because if B is invertible, then B prime is also invertible. because yeah, sorry. The basis does not have variables as coefficients, but what's the coefficient of xn plus 1? 1. So here, this is 1 is different from 0. So this basis, this matrix is for sure still invertible. We can easily compute its inverse. So what does it have to happen? Well, it has to happen that if I multiply this with the inverse, that I still have to compute. I get the identity, right? So this is B prime. This is its inverse that I want to compute. And if I multiply it with B prime, I need to get the and I'm just partitioning the inverse that I want to compute the same way as the matrix is, in order to simplify computations. So now, what do we get? Well, we have that B times H has to be the identity. So H has to be B to the minus 1. We have that B times D is equal to 0. But because B is invertible, this means that D has to be 0. We have that A transpose B H plus H transpose has to be 0, which means that H transpose is this quantity here. And then we have that 0 plus E has to be equal to 1, which means that E has to be 1. So our inverse is this matrix here. Well, which tell us, by the way, that constructing the new basis from the old one is trivial, but also constructing the new inverse from the old inverse is trivial, because the new inverse is just the old inverse with one more row and one more column, and well, the new column is trivial, and the new row I can also easily compute it, because if I already have b to the minus 1, then these coefficients here can just be obtained by multiplying b to the minus 1 with the coefficients of the constraint that I'm having. So if I have this, constructing this is trivial. Why do we want to construct b to the minus 1, b prime to the minus 1? Well, because we have to prove that this new basis that I have constructed is well feasible. And in order to see that it is well feasible, I need to show that all the reduced costs are still non-negative. And to do that, I need to compute the multipliers, and the multipliers depend on b to the minus 1. So that is why I had to construct b to the minus 1. So, what is the new vectors on multipliers? But the new vector on multipliers, by definition, is what? Is CB prime transpose B prime to the minus 1. This is how we define the vector of multipliers in the simplex algorithm. But now, so remember the definition of the space. This is the objective coefficients of the basic variables. And our new basis is just the old basis plus one more variable. So this is what we had before. And a 0 here. Because the new variable, the artificial variable xn plus 1 that we have added, does not appear in the objective. I mean, it was not there in the first place, so it is not. So its objective coefficient is 0. I multiply it by this thing here, and I get interesting. I have that the new vector of multipliers associated with this basis is the old vector of multipliers to which I have added a 0. But then the reduced costs are unchanged. Because remember, the reduced costs I obtain as C my this is how I get them, right? And in the new system, this is just with the primes. But now, the objective function did not change. The vector of multipliers is unchanged in all the constraints that I had before. And it is 0 for the new constraint. So the new constraint does not affect at all the reduced cost because its multiplier is 0. So if the basis was dual feasible before, it is also dual feasible now because the reduced costs are exactly the same. And so, but first of all, the exercise is over. And second, we had our claim, right? So the claim was that the dual simplex algorithm can easily, let's say, this property is called warm start. So it does not have to start from scratch, but it can start from the previous solution when you do some kind of changes to the problem. And one of the kind of changes that it can easily cope with is the addition of a constraint. So if you have solved a linear program and you add a constraint, you can use the dual simplex algorithm, and this algorithm does not have to start from scratch. It can start from the basis you had when you finished solving the first problem. We say that it can warm start. So you can start from where you were and keep going.
This warm start property makes useful, for instance, for reinforcement learning.
I have no idea about reinforcement learning. I hardly know what it is, but it makes a lot of sense in an application of linear programming, which is mixed integer programming.
Mixed? Okay, mixed integer
programming. Because we will see it, but the algorithm there is well, a tree search that constructs that solves a sequence of linear programs, and each linear program is obtained by the previous linear program by adding a constraint by construction. There, the dual simplex is really the obvious choice, right? Because you always have a problem solved for optimality, and you make a small modification to it by adding a constraint or more constraints. And in this case, I mean, the difference can be really orders of magnitude. I mean, if solving an LP from scratch can take, I don't know, 10,000 iterations, warm starting after you add a single constraint can take 10 iterations or 20 iterations. So it's really 3-4 orders of magnitude faster than starting from scratch. You can imagine that this makes a difference. Okay. So this is why dual is so important. I mean, if you just have to solve an LP, I mean, use the dual, use the primal, if you have only one to solve, depending on the LP, one might be faster than the other. But if you have a sequence of LPs to solve, and each of them is obtained by adding a constraint, then dual is 99.9% of the times the choice, because it can work out. Of course, it depends on the modifications that you do to the problem. If you add constraints, dual won't start. For example, if you add variables on the other end, the opposite happens. Primal can won't start, because adding a variable is, it's like saying, okay, this variable was 0 and now I can use it. So I can use the primal machinery to see whether it makes sense to add it or not to the basis. So when you add variables, you won't start with primal. When you add constraints, you warm up, you won't start with dual. It just happens that this second case here, the one of adding constraints, is way more common than the other, that dual is in practice more important. Okay? This was one exercise. Let's keep going with other exercises that are even more likely to appear in the exam. I mean, the rest of the exercises is numerical, and so it is exactly the kind of things that could end up in it. So, we are given a linear program, as usual. And we consider the feasible basis, primal feasible basis, made by variables x1 and x2. The exercise is execute one iteration of the primal simplex algorithm without the basis update. So this is a very typical exercise, right? So you're given a linear program, you're given a basis, and I'm asking you to do one iteration of the simplex algorithm. So, well, and trust me, it will never be matrices larger than 2 by 2. So, the amount of computation that you have to do by hand is always very limited. Okay, so this is our basis, because 2, 0, 2, x1, you have to pick the columns corresponding to x1 and x2, so this is our basis. So its inverse here. Okay. So we compute the basic feasible solution. So first of all, we have just confirmed that this is indeed a primal feasible basis, so we can apply the primal simplex algorithm to it. This is greater or equal to 0. And the objective value, the current objective value, is -3. How do I get -3? Well, 1/2 multiplied by 1 minus 2 times 7/4. This is just evaluating the objective at this particular point. Now, again, what's an iteration of the primal simplest algorithm? From a given basis, we have to compute the vector of multipliers. From the vector of multipliers, we have to compute the reduced cost of the non-basic variables. Check whether they are all non-negative. If they're not, pick one, do the ratio test, and figure out which variable has to be. So, in this case, this is the vector of multipliers pi, and now there is only one non-basic variable, which is x3, and we compute the reduced cost of x3. So d3 is equal to what? C3, right? So this is 0. And this is -7. So this is strictly negative. So this basis is not optimal. So x3 should enter the basis. Now we have to figure out which between x1 and x2 has to leave. Okay, let's write the ratio test. So for the ratio test, we have to compute a given column, which is b to the -1 a3. That we plug here. And the value is and this has to stay greater or equal to 0. So now we see that x2 does not impose a condition on t, because as t increases, x2 gets bigger. So the ratio test tells me that it will be x1 that has to leave. So data will be 1/2 divided by 3/2, 1/3. So x1 leaves. Right? So the new basis is x3 and x2. Again, x3 was the variable that enters, x1 is the variable that leaves, so the new basis is x3. And you could stop here. Right? Easy peasy.
Just for curiosity, was that the optimal basis, or I had to do another iteration?
I don't know. I didn't. I didn't do the next iteration. another exercise. We are given another LP, which is a little bit bigger, but not much. And the exercise is prove that basis P made by these variables here is optimal. And also, what is the corresponding basis feasible solution X, and is it the general? That's the exercise. And so here the basis is a little bit bigger. It is not 2 by 2. So computing its inverse is a little bit more complicated, but I will show you a trick that you should know, by the way. So this is the basis of which we want to compute the inverse, right? Because the variables were in the order x2, x1, x3. So if we just extract the corresponding coefficients, this is the basis P. And we want to compute the inverse of this 3 by 3 matrix. What's the easiest way to do it by hand? Is the following: is let's put an identity matrix next to it. Okay. And now we do Gaussian elimination on the first part until we get the identity here. And whatever is left here is the inverse of the basis. It's a simple trick when you do computation by hand. So, what does it mean to do Gaussian elimination? Well, I need to construct an identity here. How do I do it? Well, for example, I take this value here and I have to divide by 2 because here I want a 1. So if I divide everything by 2, I will just do it in place. If I divide everything by 2 here, I get a 1. And I have to do it in the whole row. So here I get 1/2. And then in general, you need to make sure that in the other columns, so in the other rows in this column there is 0, but here there is 0 already, so there is nothing to do. Now let's move to the next. Here there is a 0 already, nothing to do. Here there is a 1, nothing to do. Here there is a -1, and I need to turn this -1 into a 0. How do I do it? Well, I do it by adding the second row to the first, to the third, so that it becomes 0. And if I do that, this is 0, and this is 1. Yes. Okay. And again, here nothing to do. Okay, we just did. And now we move to the other one. Here there is nothing to do. Here there is nothing to do. Here there is nothing to do. Here I have the identity, and here I have my basis inverse. So this one here is b to the -1. Yeah. you know this trick. It's just you have seen Gaussian elimination in some class, right? Okay, that's Gaussian elimination. Okay, so this is my basis inverse. And now we have to prove that this basis is optimal. What does it mean? Well, we have to show that it is primal feasible and dual feasible. If a basis is at the same time primal feasible and dual feasible, then it is the optimal basis. So, well, we first compute the value of the basic variables. We get you just do this product and you get this, which is non-negative, so this is primal feasible. And now we have to check that this is dual feasible. But again, you just need to remember the definition. And if we just plug the values here, okay, we get that this is the vector of multipliers. And there is only one non-basic variable, which is x4. We have to double check that this basic variable, non-basic variable, has a non-negative reduced cost. And I mean, I'm just going quickly here. If you do the math, we get that the reduced cost is 17 over 2, which is non-negative. So this is also dual feasible. So this basis is primal feasible, is dual feasible, this is the optimal one. What is the corresponding basic feasible solution? Well, the value of the basic variables is this one, and the basic variables are x2, x1, and x3. So and the non-basic x4 is 0. So this is the basic feasible solution associated with spaces, and it is degenerate because one of the basic variables is 0. This is our definition of degeneracy, right? The dual basis basis is primal degenerate if one of the basic variables is 0. And we know that this can lead to troubles because when I do the ratio test, I divide the current value by alpha, but if the current value is already 0, then the displacement will be 0, which means that I'm changing the basis, but I'm not moving to another purpose. I'm just staying where I am, just describing it in a different way, which means that this is a degenerate iteration and I'm not improving it. Anyway, final exercise, super quick, super easy, and this also happens very, very frequently. So you have been one. You are given again a T. and you're asked to write the dual of this linear program. Okay, and this is really a trivial exercise. You just have to remember what does it mean to write the dual. So we want to derive a bound on the objective, the best possible bound on the objective, by aggregating the original constraints. And because we want to derive an inequality of the form objective greater or equal to something, then greater or equal inequalities get a non-negative multiplier, equalities in a restricted multiplier, and less or equal inequalities get a non-positive multipliers because they have the wrong sets. So the dual variables here are u1 greater or equal to 0, u2 3, and u3 less or equal to 0. These are the multipliers which will be the variables in the dual. I want to find the best possible objective, a lower bound, so I'm maximizing. And the objective, I mean, you know that the right-hand side becomes the objective. So 2u1 plus 4u2 plus u3. Okay. And now I have to write the dual constraints. And the dual constraints depend, I mean, they are conditions on the reduced cost. I know that if the variable is greater or equal to 0, the reduced cost at the optimum has to be non-negative. And if the variable is free, I know that the reduced costs have to be exactly 0, because the variable can move in both directions. So the dual constraints become what? u1 plus 2u3 less or equal to 0, because 0 is the objective coefficient of x1. Minus u1 plus u2 less or equal to 2. u2 minus u3 equal 1. And 2u1 plus u3 equal minus 3. And that's the dual. If you remember the reasoning behind it, you just write it in a couple of minutes and kind of make it work. Remember that some quick checks that you can always do to figure out whether you're writing something stupid or not. In the dual, you have a variable for every constraint in the primal, and a constraint for every variable in the primal. So if the primal has 4 variables and 3 constraints, the dual has 3 variables and 4 constraints, because the numbers are reversed. Okay, and if this is a minimization, this is a maximization, this you always get right, and things like that. So there are some easy checks that you can do in order to make sure that they are not missing anything. Okay, and one trick in order to not get these coefficients wrong is to just write the dual in this aligned form, or which is equivalent to just write the matrix. The matrix here is this one, right? So in the primal, you read it by rows. In the dual, you read it by columns. u1 plus 2, u3. minus u1 plus, did I get it wrong? There's a 2 here.
Yes.
Sorry. Plus 2u2. u2 minus u3. 2u1 minus u3. So from the matrix, okay, you cannot get it wrong. Yes?
Why the sign in the first inequality less or equal to 0?
Because we are writing that the reduced cost of variable x1 has to be greater or equal to 0. And the reduced cost is the original objective minus the aggregation. This is the aggregation, this is the original objective. It's the usual C minus U transpose A greater or equal to 0. This is C and this is U transpose A. Okay?
So if the variable was less or equal to 0, the sign would have been in the dual greater or equal.
Yes. If the variable was negative, less or equal to 0, this would be a greater or equal to 0.
Okay.
Because it's